Ever wonder how scientists figure out how molecules, like the proteins in your body, fold into their perfect functional shapes? It's like solving a puzzle where the pieces are constantly moving, twisting, and reshaping themselves. And the solution depends on tiny, invisible forces we can't even see directly. Today, we're diving into a breakthrough that's changing how we model these complex systems, using a clever twist on machine learning called normalizing flows. Let's start with the problem. Traditional methods for simulating molecular behavior, like replica exchange, are like trying every path through a maze one by one. You test countless configurations, swapping between them to find the most stable structure. It works, but it's slow, like waiting for a computer to solve a Rubik's Cube by randomly twisting each face. But here's where AI is shaking things up. Imagine a tool that doesn't just guess at solutions, but learns the rules of the game. That's what normalizing flows do. Think of them as a mathematical transformer for probability distributions. Picture a simple shape like a circle, and you want to turn it into a complicated, irregular form. Normalizing flows do this step by step, applying a series of math tricks that track every twist and turn. And here's the cool part, they're reversible. You can always backtrack to see how the shape changed. In 2022, a team led by Frank Noe used this idea to skip the tedious trial and error of replica exchange. Instead of testing every possible molecular configuration, their model learned the physics of molecular movement directly from data. It's like teaching a robot to navigate a maze by showing it a few examples. No need for hours of random guesses. So how does it work? The model starts with a simple probability distribution. Think of it as a blank canvas. Then it applies a series of transformations, like stretching or bending, to mimic how molecules might move. By training on real molecular structures, it learns to generate new, realistic shapes way faster than traditional methods. And because it's grounded in physics, the results are more accurate too. The implications. This could revolutionize drug discovery, material science, and even our understanding of life's building blocks. Imagine simulating how a drug binds to a protein in minutes instead of weeks, or predicting how a new material behaves under extreme conditions. It's like giving scientists a supercharged microscope for the invisible world of molecules. And this is just the beginning. Researchers are already using similar AI techniques to refine protein predictions, improve force fields for simulations, or design entirely new materials. The future of molecular science isn't just faster, it's smarter, more precise, and full of possibilities we're only just starting to imagine. Thanks for watching. Hit subscribe for more deep dives into the wonders of science.